Alright, welcome to Math 330. We're going to talk about Chapter 4, Section 2. This is called the method of elimination for finding solutions to systems of differential equations. So let's get started. Alright, so the best way to show you this is by an example. So let's say we have this system of equation. This is problem 1, and we have a derivative with respect to time for x and a derivative with respect to time for y. And we know that the derivative of y, the derivative of y with respect to time is equal to this. And we can actually solve this by separation of variables, and we get this value for the solution as we go through it. So we get y is equal to this, and then I can put my y back in to the derivative of x with respect to time equation, and I can now have a first order differential equation that has used the standard form or the integrating factor. In our case, the integrating factor is e to the t. I multiply that by both sides of the equations, and it comes out to be this. And then again, now it's a separable equation, and so I solve it. It looks like this. I solve for x, and now I have my x. So we have two equations and two unknowns. I don't know D and I don't know C, but if we had initial conditions, I'd be able to solve that. Now this is pretty straightforward way of solving this equation by eliminating one variable from one equation and solving that, and then using that to help solve the other equation. And it's basically what we did in section 1 of chapter 4. But what happens if our problems are a little more, let's say they have more derivatives of higher orders in them? So in the past, we've used this representation where D is equal to a derivative. It represents basically a derivative. And so we're going to do that from now. Or it could represent derivatives with respect to time or respect to position. Depends on what you're solving for. So those are simplifications of writing down what a derivative is. And then I can create this operator that the book likes to call L, which is a sum of n-order derivatives, and there's also constants in there. So the A's are constants, and the d to the n is a derivative to the nth order, so on and so forth. So I can have many orders here, and I can multiply that times my x or y. So I could have my y out here, and this would tell me that I have an nth order differential equation with respect to I. Instead of writing this whole thing out here, all I have to do is do this simple L and write it out. So what we're going to do is take a method of elimination that we used earlier and write this in a little more sophisticated form that will help us solve more challenging differential equations or systems of differential equations. So what I'm going to do is rewrite both equations in this form. So I have some derivative of x, and that's equal to some function. In this case, our function is 0. That's okay for this case, but it could be some function of time. In general, it will be a function of time. And then I have some derivative with y, and then again, it's equal to some function of h, which is some unknown function with respect to time. But in this case, our function is going to be 0, because that's the problem we did before. Now I want to represent it in my D notation in here. So for the first one. So x times 1 is that x, and x times d is that x. So I've represented my differential equation in form of this operators. Okay, and then y here has no derivative, and so its operator is just minus 3. We'll call it that case. And then if I do the same thing, so I'm going to call this d1, or d plus 1, an operator called L1, and then my minus 3 is another differential operator called L2, and this minus 3 represents this constant here, a of n, in our generalized representation of the operator. So I've created two operators, so I could write this as L1 times x L plus L2 times y equals 0. Now let's do that again for the y's. So again, my d is associated, I got a d times y, so that's a derivative of y, or y prime. And then the other operator for y here is minus 2. So d minus 2 times y gives us the same equation we have written up here, is equal to 0. Now there's no x's here. That's okay for now. So what I'm going to say is I have my first operator, L3, which is the operator with respect that would operate on x, any of these x's, but since there's no x's here, it's got to be 0. And then my L4 operator is going to be this d minus 2, which operates on y. And so what we're going to do is bring in the Wronskian idea. So the determinant of L1, so my L1 goes here, L2 operator, L2, L3, L4. The determinant times x should be equal to f of determinant of f of t, L2, h of t, L4. So you see, what I've done here is I've taken, in our case, our functions here, and since I'm trying to solve for x first, those functions go in the first column, where L1 and L2 are the operators that operate on the x variables, and L2 and L4 are the operators that operate on our y variables. So this allows me to create my solutions, or my solution for my differential equation, or my system of differential equations, to solve for the x solution first, x of t. And I can do a similar thing for y, but again, you see the difference over here is, since I'm solving for my first variable x, which is usually represented here first, x's and then y's, I have my non-homogeneous solution functions here, which could go here for when I'm solving for x, but they go over here when I solve them for y. So you basically have to write out the Wronskian for our system of equations, and then manipulate the Wronskian to get what it's equal to, a determinant over here. So let's do the math for these systems of equations. So if I plug in for my x, I plug in my L1, my L2, my L3, and my L4. I've got this determinant, and then here's my function f of t, and here's my function h of t. And I've plugged that in, and I've removed this column so that with those replaceable functions here, that's this column right here. And then now I can do this for y also, but in this case, what I've removed is this functions right here go right there because I'm solving for y. Well, let's actually find our determinants. For the x equation, we find our determinant. Remember, It's these two numbers times each other, that's right here, subtracting off these two numbers times each other. Well, 0 times 3 is 0, so I've only get this function times x. And you do the same determinant calculation here, but I got a 0 there, and I got a 0 there, so that comes out to be 0. I can do it for y, and you'll find out that I get the same equation, general equation for x is the same general equation for y. Now here's why I like this D notation, is it makes it easy to find the characteristic equations. Since you would plug in your solution, your x would be that e to the RT, and your characteristic equations would come out to be this for both. And since they're both the same, you're going to get both the same root. So what we're going to get, we'll get this as our solution for x, and we'll get this as our solution for y. I'm sorry for my drawings to cover up our solutions. But you'll notice that now I have 4 constants. So I have 4 unknowns, but only 2 equations, which I would have only 2 initial conditions. So there's no way I can find 4 constants with 2 initial conditions, so I need to find a way to get all my constants. Well, the way is those solutions have to solve our differential equations. So here's our differential equations, and here's our predicted solutions. So what we're going to do is verify that by, I'm going to take the derivative of x, that's right here, that's this part right here. I'm going to add to it a minus x, so here's my minus x term, and then I'm going to add to it 3 plus y, so here's my y term right here, and you notice this is my y, and I have 3 times that y. This is my x, so I got a minus 1 times my x, and then if you take the derivative of x, you'll get to this. So you'll notice I have only terms of e to the xt times constants and e to the minus t times constants on both, so we're going to group those terms together. So here I've got this coefficient times my x of t, or my e to the 2 t's, and I have this coefficient times my e to the minus t's. Just like in partial fractions, the coefficients on the right-hand side have to equal the coefficients on the left-hand side. So I got to make sure that this coefficient, because these have to be equal, has to equal this coefficient. And I got to make sure that this coefficient has to equal this coefficient. So if we do that, I get 2 equations with 2 unknowns. I've got my 2 equations, and if we start solving them, I find out from this equation that C1 has to equal C3. So I've taken 2 constants and made it 1 constant, because those 2 have to be equal. And from the other one, I find out that C4 has to equal 0. So now I've removed a total coefficient, a total constant, I should say. So I've removed 2, and I'm only left with 2. So in general, I can write x1 this way, and I can write y. I can write x this way, and I can write y this way, and that will be my solution to this system of equations. Now, if you go back and look at the earlier problem, you'll find out that we got practically the exact same answer. So this method works great for larger systems of equations. What we're going to do is we're going to solve a system of 3 equations and 3 unknowns, but they're first order derivatives, but it's a system of equations. So what we're going to do is figure out what our operators are. So we're going to rewrite it this way. Now, since I have 3 equations, I'm not going to have a 2 by 2 matrices. What I'm going to have is a 3 by 3 matrices, so on and so forth. If I have 4 equations, I'm going to have a 4 by 4, Or if I'm going to have 4 solutions, I need a 4x4. If I'm going to have 5 solutions, I'm going to need 5x5. In this case, I have 3 solutions. So I'm looking for x, y, and z. So what we're going to do, alright, so let's look at our operators. Well, I have an operator of d on my x. There's really only a -1 times my y and a -1 times my z. So that's these answers right here. So, and then let's look at this. I'm going to reorder these equations so it's always the first variable is x, the second variable is y, and the third variable is z. So my x operator in the second equation is -1. My y operator is a d, and my z operator is a -1. And then if we look at z, my x operator again -1, my y operator is a -1, and my z operator is d. So now I got to find my L's. So in this case, L1 is d, L2 is -1, L3 is -1. So it goes x, y, and z, 1, 2, 3. So now I'm going to do my second equation, which is L4 is -1, L5 is d, and L6 is -1. So it's 4, 5, and 6. And this is going to be 7, 8, and 9. So we're going to have 7 is -1, 8 is -1, sorry, and 9 is d. So I need to create my 3x3. So it would be L1, L2, L3, L4, L5, L6, L7, L8, L9, and then so that's my Wronskian that we can find. I should say it's like a Wronskian. It's technically not a Wronskian. And then I've reproduced this determinant over on the right-hand side, but removed the first column and replaced it with the functions. Okay, this is wrong. This should be that function. I replaced it with the function that, or what my differential equation is equal to for the first equation, what my differential equation is equal to for my second equation, what my differential equation is equal to for my third equation, or the x equation, the y equation, and the z equation. So it's e to the minus t, 0, 0, and then that column, first column, is there because I'm solving for the x. Do the same for the y, except I replace the second column of my determinant with the solutions to those differential equations, or what those differential equations are supposed to equal. And then I do the same for z. And now we have to find the determinants. So let's find the determinants. So this is for x. So there's my first determinant. Now the way we're going to find this determinant is I'm going to recopy these first two columns over to the right-hand side here, and then I'm going to draw lines. So the lines that go down like this, I multiply these three, and this is positive, so I get a d cubed, and then I do an up line. Well, since I'm going up, these are negative, and so I multiply these three, so I get the multiple of these three is positive d, but it's negative since it's going up. And then I multiply these three, it gives me a -1. And then I do the ones going up. That's going to be another negative d, because this is going to be a positive d, but going up is negative. And then I'm going to do this. That's going to be another negative, and that's added to this. And then I'm going to do another up, and this is going to be a positive d, but it's negative value here. So if we add all these up, I get this as a determinant for our first determinant. And now I want to find my second determinant. Okay, so the first one is going to be d squared times our exponential. The second one's going to be a plus 0, because we got a 0 there, or a minus 0, I should say. Now that's going to be 0 again also. This one's going to give us a minus e to the minus t. This one's going to give us plus 0. And then the last one's going to give us a plus 0, or a minus 0, since it's going up. And if we add all these up, these give us 0. So our differential equation looks like this now. So we have to solve that one. Now we got to do the same thing for the x's and y's, where we go through the same processes. Now this for the y's, this is the same solution that we did earlier, so I'm not going to repeat that. I'm just going to find the determinant for the right-hand side now. So that first one is 0, the second one is 0, the third one is that value, so on and so forth as we go through here. So if we look at this, I have an e to the minus t here, a negative e to the minus t, that's 0. And then I have the derivative of something, but it's derivative of a constant, because there's, where I got this right here, it's a derivative of a negative 1. So that's going to be 0. So our answer is 0 again, and we get the exact same equation that we had for x. And now let's look at the z1. Again, we've already found the determinant of this. It's this answer. So I want to find the determinant for this one. So I go through my routine. That's going to give me 0. That's going to give me positive derivative of e to the minus t. This is going to be 0. That's going to be 0. That's going to be a positive e to the minus t. And that's going to be 0. And look at this. I've got the derivative of e to the minus t, which is a minus e to the minus t, added to a positive. So again, that adds up to 0. So I get the same differential equation with respect to x, y, and z. So if we solve, we get the characteristic equation, and we solve that, we find that we have repeated roots of minus 1 and a root of 2. So that's going to give us this solution. But look at that. I've got 3 equations and 9 constants I have to find. Well, how do I find them? Well, we have to solve lots of algebra. So how would we do it? Well, we do it the same way that I showed you earlier. We have to plug these solutions back in to these differential equations and figure out, make the constants on the left-hand side equal the constants on the right-hand side. So let's work on the z1 first. So there's my z prime. There's my plus x, or my x, and here's my y. And you'll notice I only have exponentials of e to the minus t, e to the minus t, and e to the 2t. And they're the same functions on both sides. Okay? So I'm going to group constants. So there's my constants for the left-hand side. Here's my constants for the right-hand side. And so I have to make sure that this constant and this constant are equal. And so I'm going to do that. There they are. There's my first equation. There's the constants for the t, e to the minus t part. And there's my constants for e to the minus 2's from the x equations. Now I'm going to do the same thing for the y, the derivative with respect to y. There's my derivative with respect to y. There's my x, and there's my z. Okay? I'm going to group my constants back together, and if I do that, I get another series of 3 equations. There's my equations for my e to the minus t's, my constants that equate the constants of e to the minus t's. There's my equation equate the constants from the t, e to the minus t's. And there's my constants that relates e to the 2t's. And then I'm going to do my x equation. So here is my x equation right here. Here is the derivative with respect to x. Here is my y. Here is my z. and here is the last term, the e to the minus t, and now I'm going to group my constants together. Here they are, and so here's the constants for the e to the minus t's. Here's the constants, and sorry for their overlapping, here's the constants for the e to the, the t times e to the minus t coefficients. And then here's the constants for the e to the 2t's. Now I have 9 equations and 9 unknowns. And so we got to solve to figure out how these constants are related. So here's what we have to solve. I have to figure out how these constants, I have my 9 equations. This is going to be a challenging solution. I would recommend using linear algebra if you know how to use linear algebra or know how to do this with Maple. So what I did is, this is equation 1, this is equation 2, this is equation 3, this is equation 4, this is equation 5, this is equation 6, this is equation 7, this is the equation 8, and this is equation 9. And I put all these equations into Maple, and then I used this exact command right here, and I said solve for these 9 variables, and this is the solution that Maple came back with. Okay, so from the solution we can determine that C3 equals C9, C6 equals C9, and C9 equals C9. So what this tells me is that C3, C6, and C9 all have to be the same number. So I've basically taken 3 coefficients and put it into 1. So we're going to claim that C3, all these are equal to C3 right now. So I can go back in here, and this is a C3, this is a C3, and this is C3. So those are all the same. My next one is, it gives me C2 has to be 2/3, C5 has to be a negative 1/3, and C8 has to be a negative 1/3. So I can put those in there. So I've eliminated 3 more coefficients. So I've taken 6 equations so far, and I'm down to 1 coefficient. I've only got 4 left. So from this, so for my next one, I find out that C4 has to equal C4 and C7 has to equal C7. So those are the last 2 coefficients. And from this, we can figure out that C1 equals this. So if I so I'll leave C7 and C4, and I'll replace C1 with our expression down here, and I get an X equation that's equal to that, a Y equation that's equal to that, and a Z equation that's equal to that. And now I have 3 unknowns and 3 equations. So I only need 3 initial conditions. I need the initial value of function x at t equals 0. I need the initial value of the function of y at t equals 0. And I need the initial value of the function of z at t equals 0. And I can predict what happens to this system into the future. All right. Whew. That took some work. Well, this was a challenging problem, and I showed you the challenging problem so that you could see how it worked for if you had more than just a system of 2 equations. But that's it. I hope you understand how to use this operator method and the elimination method with these determinants to solve a system of equations. And I'll see you in class. Bye.